Hello and welcome to this presentation related to linear motion and introduction. In this presentation we're going to outline some definitions in terminology associated with linear motion, such as distance and displacement and speed and velocity. This distinction often becomes conflated within much work we undertake where we're considering straight line linear motion. For example, if we consider a cyclist riding in a straight line from position A to position B, in that particular instance the distance travelled would be the same as the displacement. But obviously this straight line linear motion does not always occur. So sometimes we need to be very clear on the distinction between distance and displacement. The same considerations can be applied to speed and velocity. So after viewing this presentation, hopefully you'll be able to decide whether the 30 mile per hour speed limit we often see while driving on the roads is a speed limit or is it a velocity limit. Let's commence the presentation. Here's a brief overview of the presentation. We commence with some definitions defining distance, displacement, speed and velocity, and in this section we have exercises 1 and 2 to complete. Next we consider some conversions from meters per second to kilometers per hour and vice versa. We undertake exercise 3. Next we have an overview of the velocity versus time diagram. Then we define acceleration and complete exercise 4. And then we consider some examples. Example 1 calculates the average or mean average speed for a given problem. Example 2 calculates the distance travelled for the given problem. And we use example 3 to specifically highlight the difference between the distance, the scalar property, displacement, the vector property, and again with speed, the scalar property, and velocity, the vector property. So we emphasise the difference between these various quantities within example 3. Presentation overview continued. Now we have an array of exercises to attempt. Exercise 5, we have to calculate the average speed, symbol V. Exercise 6, we have to calculate the average velocity, also symbol V. Exercise 7, we calculate both the average speed and the average velocity, symbol V. Exercise 8, we calculate the average acceleration for a given problem, symbol A. Exercise 9, we calculate the time taken, lowercase t. Exercise 10, we draw the appropriate vector diagrams and calculate the distance and displacement. Exercise 11, we calculate the velocity, stroke speed, for the given problem and also the acceleration. Finally, we're left with some tutorial questions to attempt at our own pace. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note they are only approximate start times, usually rounded to the nearest minute. We're going to outline some of the basic terminology and formulae used when calculating distance and displacement, speed and velocity, and acceleration. Firstly, let's consider the difference between distance and displacement. So distance here is defined as the length along the path of an object, whatever the form of the path. Within this handout, distance predominantly relates to straight line motion. In contrast, displacement is the distance of a body's final location from its initial starting point. So in the diagram, the dotted line A to B indicates the displacement, this line here. Displacement is as the crow flies, so it's the shortest distance between A and B here. And the solid line AB indicates the distance travelled. So this is the distance travelled from A to B. Note that if a body returns to the starting point, its displacement is 0, but the distance travelled will not be 0. So in essence, distance is a scalar quantity and displacement is a vector quantity. Let's consider speed and velocity. So for many quantities, their direction is just as important as their magnitude, their size or value. There's no good driving fast if we do not know where we are heading. So there are two terms used to distinguish between scalar and vector quantities that relate to movement. So these are speed and velocity. Speed is a scalar quantity, velocity is a vector quantity. Exercise 1 asks us to state the difference between a scalar quantity and a vector quantity. We reviewed this distinction in a previous presentation related to scalar and vector properties. So a scalar quantity has a magnitude but no direction, and a vector quantity has both a magnitude and direction. So speed is defined as the rate of change of distance with respect to time. This is the scalar quantity. So a pedestrian walking along a path at 4 kilometers per hour. We have a magnitude there but no direction. So average speed, symbol V, is defined as distance travelled divided by time taken. In symbol form, that's denoted as S divided by T. And velocity is the rate of change of distance with respect to time in a stated direction. That makes it a vector property. So for example, the ship is cruising at 30 knots in a southwesterly direction. That's a vector property. The magnitude is 30 knots and the direction, of course, is southwesterly. So velocity, again symbol V here, is now defined as displacement divided by time taken. Symbols again S divided by T. Exercise 2 wants us to define the SI unit of speed and velocity. Speed and velocity have the derived SI unit of the meter per second or meter second to the negative 1. Let's consider an alternative unit for speed and velocity. So we know that both speed and velocity can be stated in the unit of meter per second, but also can be stated in the unit of kilometer per hour. To convert from one measure of unit to the other, the following conversions are used. Just note that in 1 hour there are 60 times 60 seconds, so 3,600 seconds in 1 hour. So to convert from kilometers per hour to meters per second, we multiply the kilometers per hour by 1000 divided by 3600, and that will change the unit to meters per second. Or to convert from meters per second to kilometers an hour, we multiply our value in meters per second by 3600 divided by 1000, and that converts the speed or velocity into kilometers per hour. So example 1 here, we're going to convert 50 kilometers an hour into meters per second. So we simply multiply the 50 kilometers per hour by 1000 divided by 3600. That evaluates to 13.9 meters per second. Example 2 here, if we want to convert 4.7 meters per second into kilometers per hour, then we multiply the 4.7 meters per second by 3600 upon 1000. In this case, that's 16.92 kilometers per hour. Exercise 3, Part A. A cheetah has a top speed of 100 kilometers per hour. We've got to convert this speed into meters per second. And Part B. An Olympic sprinter has a maximum speed of 10 meters per second. We have to convert this into kilometers per hour. Answers shown in the bracket here. For ease of reference, here are the various conversions required. I'll let you choose the appropriate conversion to solve parts A and B, but the solutions are shown on the following slide. Here's exercise 3 solution. Part A relates to the cheetah. 100 kilometers per hour converted to meters per second. It's 27.78 meters per second to 4 significant figures. Part B was the sprinter. 10 meters per second, this time converted to kilometres an hour, so it's 36 kilometres per hour. Just for reference, here are the unity brackets used to develop the conversions shown on the previous slide. Unity brackets are a very useful method for structuring such conversions. Unity brackets are shown within these rugby posts, as some students term them. And always remember that these are cancelling unity brackets. So we cancel the kilometres with the kilometres here, the hours with the hours here. And this leaves us with the conversion. And this first conversion relates to changing kilometres per hour into metres per second. And using a very similar process below, again, cancelling the units, we can show the reciprocal conversion here for converting metres per second to kilometres an hour. So that's just background reference for information of how the various conversions on the previous slide are actually derived. There is a separate presentation related to the use of unity brackets for your further reference. Let's briefly consider the velocity time diagram, shown here. Velocity on the vertical axis, time on the horizontal axis. Note the general notation used. Symbol U denotes the initial velocity, meters per second. Symbol V denotes the final velocity, again in meters per second. Symbol T is the time taken, and that would be in seconds. Note some characteristics of the graph. The area under the graph for straight line linear motion relates to distance travelled, symbol S, although generally speaking the area under the graph actually relates to displacement, but when we're considering straight line linear motion, which we are in these notes, distance is the same as the displacement, but do be careful, the actual area under the graph does relate to displacement. So though I always state in these notes area under the velocity time diagram equates to distance travelled, that really is displacement. Another useful characteristic of the velocity time graph is that the gradient of the line relates to the acceleration. Note the gradient of the graph relates to constant acceleration here as the velocity changes from u to v. So those are two very important characteristics of the velocity time diagram, and this knowledge helps us solve various kinematic problems. Note that acceleration may be stated as a scalar quantity or a vector quantity. Acceleration relates to the rate of change of velocity with respect to time. So acceleration, symbol lowercase a, is the change in velocity, v minus u in symbol form, shown here on our diagram, divided by the time taken, lowercase t, shown here on our diagram. So essentially we're finding the gradient of this right-angled triangle in this particular case. Exercise 4 here. Acceleration has the SI unit of the meter per second squared, which can be written as meters second to negative 2. And again, this is a derived unit. Just note for reference, when speed or velocity is increasing, the acceleration is positive. When speed or velocity is decreasing or directed towards the origin of the motion, the acceleration is negative. Also note that decreasing acceleration is sometimes termed a retardation or a deceleration. Just some basic terminology there to be aware of. Let's consider example 1. A cyclist completes a road race of 42.2 kilometers in 2 hours 36 minutes. Part 1, we have to find the average speed of the cyclist in kilometers per hour, and part 2, we've got to convert this speed into meters per second. So here's part 1 solution, finding the average speed of the cyclist. We know the distance travelled was 42.2 kilometers. Time taken was 2 hours and 36 minutes. Notice I've converted that into a decimal here, so that's 2 plus 36 divided by 60. There are 60 minutes in an hour, so that evaluates to 2.6 hours. For reference, here's the use of unity brackets to structure our conversion. So we're converting 2 hours and 36 minutes into hours. So the unity bracket used here is 1 hour is equivalent to 60 minutes. Remember, these are cancelling unity brackets, so we have to cancel the minutes to leave us with hours. This is the conversion from minutes to hours, of course. We find that 2 hours 36 minutes in decimal is 2.6 hours. For your reference, there is a separate presentation related to the use of unity brackets. So to find the average speed V is simply the S, 42.2, divided by T, 2.6. So the average speed is 16.23 kilometers per hour. Part 2, we have to convert this speed into meters per second. So V is equal to 16.23 kilometers per hour multiplied by 1,000 divided by 3,600. So 4.51 meters per second. Let's consider example 2. A motor car travels at a constant speed of 50 kilometers per hour for 2 minutes. We've got to calculate the distance travelled in meters. So from the question, V is equal to 50 kilometers per hour. I've converted that here into meters per second. The time taken T is 2 minutes, and here converted T into seconds, 120 seconds. Speed is equal to distance travelled divided by time taken. We can rearrange for the distance travelled, symbol S. That's V, 13.89 meters per second, multiplied by time T, 120 seconds. So the distance travelled is approximately 1,667 meters. Let's consider example 3. A train commences its outward journey from station X to station Y by travelling 40 kilometers due north and then 30 kilometers due east. What distance did the train travel, and what is its displacement from station X when arriving at station Y? If the train takes the reverse journey back to station X, what now is its distance travelled, and what now is its displacement from station X? So here's example 3 continued. This is the beginning of the solution. Just note we have drawn here a vector diagram, and in this particular diagram this is actually a right-angled triangle. The train starts from station X and travels due north 40 kilometers and then continues due east 30 kilometers. It arrives then at station Y. Just notice for reference we will calculate the displacement shown here using Pythagoras' theorem. We've reviewed Pythagoras' theorem in a previous presentation. So example 3, solution continued. So part A, we're considering the outward journey from station X to station Y. So the distance travelled, symbol S, would be 40 plus 30, that's 70 kilometers. That's this distance here of 40 kilometers, then we add 30 kilometers to it to arrive at station Y. And the displacement, also symbol S, here, is calculated using Pythagoras' theorem, as shown above here. So the displacement of Y from X is 50 kilometers. So notice an example here of how distance and displacement are actually different quantities. Example 3, solution continued. Part B, we're now considering the return journey from station Y to station X. So now the distance travelled S is actually 70 kilometers for the outward journey from X to Y, and of course it's 70 kilometers for the return journey from Y to X. So the total distance travelled is 140 kilometers. However, for the displacement, symbol S, the value is 0 as the train has returned to its starting point. So by definition, it has no displacement from its origin. So again, notice a difference there between distance travelled and displacement. They are actually different quantities. As example 3 continued, What I'm going to try and show you now is some diagrams to try and indicate how the parameters of distance, displacement, speed and velocity would be drawn on the respective diagrams. So on this diagram I have a distance versus time diagram. And just for convenience I've made the assumption that the journey from X to Y on our diagram takes 1 hour. So from station X here through to station Y takes 1 hour. And of course the journey from station Y to station X is also assumed to take 1 hour. So plotting distance, symbol S, I'm using kilometres here because that was the unit used in the example, and I'm plotting against time here, symbol T, using hours, and again that's the unit used in the example. We will plot this linear line shown here on the diagram, and I'm indicating the 70 kilometres distance here, which relates to the distance from X to Y on a diagram, and the 140 kilometres distance relates to the return journey back from station Y to station X. Note the gradient of the line here is actually the mean speed in this case, denoted V mean. That's the average speed. So we can clearly see from this distance time diagram that the total distance travelled was 140 kilometres from station X to Y and then from station Y to station X. And note for reference for the value stated in the diagram below, the average speed calculates to be 70 kilometres per hour. Example 3, continued. Let's now consider a displacement versus time diagram. Here displacement is plotted on the vertical axis, again symbol S, unit the kilometre, time on the horizontal axis as before. But note this time a slightly different shape to the diagram. We commence from zero displacement as the train travels from station X through to station Y, and at station Y we have a displacement of 50 kilometres. But note now the gradient of the line changes its sense. From the return journey from station Y to station X, the displacement decreases back to 0 when we're again at station X. So considering the gradient of the line between X and Y, this is a positive gradient, and that relates to a positive mean velocity in this case. However, the gradient of the line between stations Y and X is now a negative gradient, so the velocity now will be in a negative sense. And for reference for the values used in the diagram below, the average velocity calculates to be 50 kilometres per hour. And again, this relates to the fact that the displacement is actually a vector quantity. So displacement is increasing as we move from X, the origin of the travel, to Y, but displacement decreases as we move from Y back to the origin, X. So for reference, note the difference between the displacement time diagram shown here and the distance time diagram shown here. Example 3, continued. So on the previous slides we considered the difference between distance and displacement, our scalar and vector property. We can now undertake a similar exercise to compare speed and velocity. So here is a speed versus time diagram. We have speed, symbol V in kilometres per hour on the vertical axis, and again we have time t in hours on the horizontal axis. The mean speed, denoted as V mean here, could be calculated from the distance time diagram. Let's assume it's a constant speed between station X and Y, and also a constant speed between station Y and X, the reverse journey. So the gradient of this line is 0, is a horizontal line indicating that it's a constant speed. In other words, we are not accelerating. Obviously this average speed or mean speed is a fictitious value because we realise that the train would have to accelerate and decelerate at certain points of its journey. But for ease of illustration here, we will assume the train speed is constant throughout its entire journey. And as we said previously, the area under a speed-time diagram relates to distance travelled. So for outward journey from station X to station Y, the train travels 70 kilometres, and of course for our return journey from station Y to X, we again travel 70 kilometres. So the total distance travelled by the train is 140 kilometres. Example 3 continued. Here's our velocity time diagram. So now we have velocity, symbol V, plotted on the vertical axis in kilometres per hour, and again time t on the horizontal axis. So plotting the train's mean velocity between station X and station Y, and then plotting the mean velocity between station Y and station X. What we notice here is the gradient of the line is 0 because it's assumed constant velocity between station X and station Y, but notice this is a constant positive velocity. Between station Y and station X, the gradient of the line is still 0, it's not accelerating, constant velocity, but this is a constant negative velocity. So we have positive mean velocity between station X and Y in our assumed first hour of travel, but we have negative velocity, negative V mean, during our travel from station Y to station X, our second hour of travel. So we can see in this diagram how the vector quantity of velocity affects the drawing of the diagram. The velocity of the train from X to Y is a positive velocity, but the direction is reversed from Y to X, so that becomes a negative velocity. So velocity has the vector property. So again, notice the difference between the velocity time diagram shown here and the speed time diagram shown here. So speed is a scalar quantity. It has the characteristics of a scalar property. Velocity is a vector quantity, so it has the characteristics of vector property. As we mentioned earlier in the presentation, the area under a velocity time diagram relates to displacement. So we have the positive 50 kilometer displacement from X to Y, but the negative 50 kilometer displacement from Y to X. Hence the overall displacement from X to Y and Y to X is 0, because the final position of the train is the same as its starting position. Let's consider exercise 5. During a journey of 80 kilometers completed in 1 hour 30 minutes, a motor car reached a speed of 140 kilometers per hour. Calculate the average speed for the journey in kilometers per hour and explain the difference between the average speed and the maximum speed. I'd encourage you to stop the presentation and attempt exercise 5, but a full solution is shown on the following slides. Exercise 5 solution. So distance travelled is 80 kilometers. Notice the time stated in the question is 1 hour 30 minutes. That's been converted into decimal here, 1.5 hours. So to calculate the average speed, symbol V, is simply S divided by T. So the average speed calculates to be 53.33 kilometers per hour to 4 significant figures. Exercise 5 solution continued. To try and explain the difference between the mean average speed, calculated on the previous slide, and the maximum speed given in the question, I'm going to use this velocity time diagram. What the diagram is trying to show is that the mean or average speed is constant throughout the time of the journey, indicated by this horizontal line, and essentially the area under the horizontal line is in theory the same as that underneath this red line, because the displacement, or in this case distance travelled, should be the same. So the average velocity or average speed is essentially a fictitious value. It assumes the vehicle remained at the constant speed of 54.3 kilometers per hour in this case throughout the entire journey, which we know of course is not practical. Exercise 5 solution continued. So essentially the difference between the maximum speed and the average speed is overviewed here. The maximum speed during the journey The speed of the car varies due to traffic jams, stop signs, traffic lights, etc. So the maximum speed can be considered the peak speed that the vehicle achieved during the entire journey. This is an instantaneous speed. In other words, it occurs at a particular instance, but it can occur more than once within the journey. Considering average speed, if the car travelled at this average constant speed of 53.3 kilometers per hour for the entire journey, it would have completed the 80 kilometers in 1.5 hours. The calculation of the average speed can be useful as it provides an estimate as to the rate at which the journey was completed. Exercise 6. A ship sails northeast for a distance of 60 kilometers in 2 hours. We've got to calculate the average velocity in meters per second. Answer stated in the bracket here. To start the presentation, attempt exercise 6, but the full solution shown on the following slide. Exercise 6, the solution. The distance travelled is 60 kilometers, so that's 60,000 meters. The time taken was 2 hours, so multiplied by 3,600, that's 7,200 seconds. So the average velocity v is simply the distance travelled s divided by the time taken t. Inserting the values, the average velocity is 8.3 recurring meters per second. Note the dot above the 3 means recurring number. Exercise 7. A cyclist completes a race of 42.4 kilometers in 2 hours 12 minutes. If the finish of the race is 12 kilometers due west from the start point, we've got to calculate the average speed and the average velocity of the cyclist in kilometers per hour. Answers shown in the bracket. I encourage you to start the presentation and attempt exercise 7, but the full solution shown on the following slides. Exercise 7, commencement of the solution. So notice in exercise 7 we're actually given the distance travelled, s, 42.4 kilometers. Here's a diagrammatic view of the distance on my sketch from A to B. That's the 42.4 kilometers distance. And also the displacement, symbol S again, 12 kilometers due west. Displacement shown here from A to B, 12 kilometers displacement due west. Time taken was 2 hours and 12 minutes, stated in the question here. So we need to convert that to decimals, so that's 2 plus 12 divided by 60. Don't forget there are 60 minutes in an hour. So that calculates to the time taken is 2.2 hours using decimals. We can first of all calculate the average speed. Note the formula for speed is distance divided by time taken. So in this case the average speed v calculates to be 19.27 kilometers per hour. Just notice the dot above the 2 and the 7 means these numbers are recurring. And exercise 7 solution continued. Same information extracted from the question, but this time we're calculating the average velocity, again symbol v, but the formula this time is displacement, that's the 12 kilometers due west, divided by the time taken, the 2.2 hours. So the average velocity v calculates to be 5.45 kilometers per hour due west. So note the difference between the average speed and average velocity. Here the average speed is given in terms of a magnitude only, just a value. Here the average velocity is stated in terms of a magnitude and a direction. Exercise 8. The speed of a motor car increases from 15 kilometers an hour to 75 kilometers an hour in 6 seconds. We're asked to sketch the velocity time diagram and calculate the acceleration in meters per second squared. The answer is stated here in the bracket to 4 significant figures. I'd encourage you to start the presentation and attempt exercise 8, but the full solution is shown on the following slides. Exercise 8, here's the commencement of the solution. Extracting the information from the question, the initial speed is 15 kilometers per hour, that's symbol U here, converted immediately into meters per second. That's 4.16 recurring meters per second. The final speed is 75 kilometers an hour, symbol V here, and again converted into meters per second, 20.83 recurring meters per second. The time taken given in the question is 6 seconds. Lowercase t here, 6 seconds. Exercise 8, solution continued. The top diagram here shows the sketch of a velocity time diagram. Velocity v in meters per second, plotted on the vertical axis. Here's the initial velocity, here's the final velocity, and the time in seconds on the horizontal axis. Duration of the motion in exercise 8 is 6 seconds. Note, as we outlined previously, the slope or the gradient of the line on a velocity time diagram is the acceleration. So the steepness of the line here is actually acceleration, so in our increasing speed over the 6 second duration. And for reference, the area under the graph relates to displacement or distance travelled. And for further reference, I've just sketched below the acceleration time diagram, acceleration on the vertical axis in meters per second squared, time again on the horizontal axis. Note that the horizontal line on this diagram indicates the constant acceleration over the 6 second time period. This horizontal line here is the acceleration, which we're now going to calculate below. The area under the graph actually equates to change in velocity. So let's now calculate the acceleration, A, using the formula we stated previously, which is v minus u divided by t. Inserting the values from the previous slide, notice there are recurring numbers here. The linear acceleration calculates to be 2.7 recurring meters per second squared. And of course, that's the gradient of this line here. Exercise 9. The brakes of an electric locomotive are applied when travelling at 170 kilometers per hour. The brakes retard the locomotive at a rate of 1.8 meters per second squared. We're asked to sketch the velocity time diagram and determine the time required to reduce the speed of the locomotive to 100 kilometers per hour. Answer stated in the bracket here. Again, I'd encourage you to start the presentation and attempt exercise 9, but a full work solution shown on the following slides. Exercise 9, here's the beginning of the solution. So from the question, the initial speed u is stated as 170 kilometers per hour. That's been converted here into meters per second. It's 47.2 recurring meters per second. The retarding rate is given as 1.8 meters per second squared, so that's the acceleration, but it's a negative acceleration because it's retarding or decelerating. That will be negative 1.8 meters per second squared, so that's deceleration. And the final speed v, stated in the question, is 100 kilometers per hour, and again immediately converted into meters per second, so that's 27.7 recurring meters per second. Exercise 9, solution continued. So here's the sketch of the velocity time diagram. Initial speed 47.2 recurring meters per second. Our final speed 27.7 meters per second. So from the acceleration equation, a is equal to v minus u divided by t. We simply now rearrange for time taken, t, and that's v minus u divided by a. Inserting the values, that evaluates to a time taken t of 10.80 seconds to 4 significant figures. Just note for reference, when calculating this part of the equation, numerator, that becomes a negative value, and we're dividing by a negative value in the denominator. Hence, that's why we obtain a positive time taken. Exercise 10. A lady cycles 24 kilometres due south and then 20 kilometres due east, whilst a man, starting from the same place as the lady, cycles 32 kilometres due east and then 7 kilometres due south. We're asked to draw the vector diagrams and determine the distance and displacement each cyclist travelled on their respective journeys. So here's the lady's distance and displacement. Here's the man's distance and displacement. I encourage you to stop the presentation and attempt exercise 10, but a full solution shown on the following slides. Exercise 10, here's the commencement of the solution. Here's our vector diagram. It shows the lady travelling 24 kilometres due south and 20 kilometres due east. The diagram also shows the man travelling 32 kilometres due east and 7 kilometres due south. Here are the displacement vectors for the lady and for the man. So exercise 10, solution continued. So considering the lady's journey, here's the distance the lady travelled, simple S. We simply add the 24 to the 20, get 44 kilometres. So this is the 24, add 20, but the calculate is displacement. We use Pythagoras theorem, so displacement of the lady, simple S again, is 24 squared plus 20 squared, all square rooted. So displacement is 31.24 metres in 4 significant figures. We undertake the same exercise for the man's journey, but here's now the distance the man travelled. It's 39 kilometres. And here's the displacement for the man, simple S here, calculated using Pythagoras theorem again. And that evaluates to 32.76 metres to 4 significant figures. If the acceleration is assumed constant, we have to calculate A, the final velocity, B, the acceleration, and C, the speed of the vehicle after 45 seconds. I'd encourage you to stop the presentation and attempt exercise 11, but a full work solution is shown on the following slides. Exercise 11, commencement of the solution. So extracting the information from the question, the acceleration occurs over a distance of 720 metres. So S is 720 metres in our diagram here. The time duration is 1 minute. So T is going to be 60 seconds. And we know the initial velocity, symbol U here, that will be 0 because the vehicle starts from rest. So part A, we need to calculate the final velocity. Solution continued. To calculate the area under the graph minus the initial velocity multiplied by the time taken, given in the question, divided by 2. Just note for reference, this is the standard formula for calculating the area of a trapezium. But I'm going to rearrange the equation to find V. So to transpose the equation, I'll multiply throughout by 2, divide throughout by t, and then subtract u from both sides of the equation. So inserting the values, the final velocity v is 24 meters per second. Just note for reference, I converted the 24 meters per second into kilometers per hour using the appropriate conversion. So that's 86.4 kilometers per hour. Obviously, we can clearly see that the area under this velocity time diagram is that of a triangle, so we could have calculated the area simply by the equation Vt divided by 2. In other words, half base times height, the formula for the area of a triangle. Exercise 11, solution continued. Here's part B. We have to calculate the acceleration A. That's the gradient of the line on the velocity time diagram. And to do that, we'll use the equation v minus u divided by t. Inserting the values for v and u and t. The acceleration is 0.4 meters per second squared. Exercise 11, solution continued. Finally, here's part C. We're going to calculate the speed after 45 seconds. So again, from the equation, A is equal to V minus U divided by T. I'm going to transpose the equation for V, the final velocity or the final speed. So multiplying both sides by T, and this time adding U to both sides of the equation, we transpose to the form V is equal to AT plus U. So inserting the values, V is equal to 18 meters per second. And again, V is being converted to kilometers per hour. Finally, I'll leave you with some tutorial questions to attempt at your own pace. Here's question 1, 2, and 3. Answers are shown in the brackets. And here are further questions, question 4, 5, question 6. And again, the answers shown in the brackets. I'd encourage you to stop the presentation and attempt these questions. So hopefully now you can answer the question posed at the beginning of the presentation as to whether the 30 miles per hour speed limit is a speed limit. Well, yes, it is described correctly as a speed limit because there is no direction associated with the restriction. Here's the bibliography used to help generate the presentation. Unfortunately, part of the presentation is from an unknown reference source, so my apologies in this case. Hope this has been of interest to you, and thank you for viewing.